Alright, hello everyone. So this is the next installment of the Physics 121 videos. Today what we'd want to do is we want to see if we can actually use the Biot-Savart law to calculate magnetic fields due to different arrangements of currents. So let me remind you what we had worked out in the last video. We imagined a wire carrying some current I, and we considered one little segment of that wire. And we defined a delta S vector, which had a magnitude equal to the length of this segment and a direction that was in the direction of the current. And then we went from that segment to some observation point P, and we were going to try to calculate the magnetic field at that point P. So by the right-hand rule, what we would have in this situation is a magnetic field that would be pointing out of the page, and the distance from our observation point to the current segment is r, and we also had a unit vector r hat that pointed along the line connecting the current segment and the observation point. So with all of that, what we had worked out is that the magnetic field at point P, due to this little current segment, was given by some constants, and then there was the current, and it was delta S, and we had also defined this cross product where the magnitude of this cross product is the magnitude of the two vectors, but r hat is just a unit vector, so its length is 1, so we end up with just the magnitude delta S. And then the cross product had the sine of the angle between the two vectors. And so if delta S is along the direction of the wire, and theta, let me see if we can make that a bit bigger. Theta is this angle between the current direction and r hat. Okay, the direction of delta S cross r hat was given by, delta S cross r hat was given by what we called right-hand rule number 2. And so just in words, what we did is we put our arm in the direction of the first vector, in this case delta S, so that's along the wire, and then we curl our fingers so that they are parallel to the second vector r hat, and the thumb of our right hand will point in the direction of the magnetic field, which in this case is out of the page. Okay, so let's see if we can do our first application. So magnetic field due to a long straight current. So the geometry of this problem is going to be, let's imagine we have some y-axis and then we have an x-axis that's horizontal. I'm going to take a wire and I'm going to place it on the x-axis like this, and our wire is going to have a length L, so that I'm going to choose to have one end of the wire at x equals minus L by 2 and the other end of the wire at x equals plus L by 2. And we're going to try to calculate the magnetic field at a point P that sits on the y-axis, and we'll make that point P a distance d from the x-axis. Okay, so let's assign a direction for the current, and so we'll say the current is going along positive x. And so what we could do right away is we could do right-hand rule. We could put our thumb in the right-hand rule number 1, let's say. We put our thumb in the direction of the current, the thumb of our right hand, and our fingers curl around the wire. So at all points directly above the wire in the xy plane, the magnetic field is coming out of the screen. Okay, so what we could say is that the magnetic field at point P is coming out of the screen. Okay, so if we want to do this using the Biot-Savart law, what we're going to do is we're going to take a little segment of our current carrying wire, and we'll say, all right, at this segment, there is a vector delta x. I'm going to, instead of delta s, I'm using delta x because it's along the x-axis. All right, and then we need to know the distance from our current segment to our observation point. And so let me call this Ri. I'm going to call it Ri because this is going to apply to segment I. Okay, and so then we also have like a r hat I, which is our unit vector r hat I. And then we have the angle between our delta x and our r hat is theta I. Okay, the other thing that we need is to say that this distance is x from the y-axis to our observation point is distance x. And so let me just color in this little segment of current. So that's our current segment that we're working with. Okay, so maybe the first thing we could do is we could say, well, let's see, Ri is going to be equal to, let me label this xi, because that would be different for our different segments. Oops. Notice that we have a, I don't know which, sorry. So we have a right angle triangle here. The right angle triangle is d, xi, and ri. And so by Pythagoras Theorem, ri is equal to the square root of xi squared plus d squared. Okay, and so then we have over here, this was the angle theta I. So inside we have the angle 180 degrees minus theta I. Okay, so our Biot-Savart law, let's look up here, is I delta s, which we're going to say delta x, cross r hat over r squared. So let's start to write down this Biot-Savart law. And so this is going to be just for segment I. So this is the magnetic field not due to the whole wire, but just for the one little current segment that we're thinking about right now. So it's mu naught I over 4 pi. Then it's delta x cross ri hat divided by ri squared. Okay, so we already worked out that the magnetic field direction, so let's say this is the magnetic field just to the segment I, is coming out of the screen. And so let's just denote that our z-axis is out of the screen. So that's the k-hat direction. If I hat is to the right and j hat is to the top of the screen, then k hat is out of the screen. So this delta x cross ri hat is equal to the magnitude of delta x times the sine of theta I, and then it has a direction which we've determined is in the k-hat direction. Okay, so then the magnetic field is mu naught I over 4 pi delta x sine theta I. Ri squared is xi squared plus d squared, so we get a xi squared plus d squared, and then we said our cross product is in the k-hat direction. Okay, the next thing we have to do is we have to work out a convenient expression, a convenient way to write down sine of theta I. So the first thing I want to note is that there's a trig identity that we can make use of, where sine of theta I is equivalent to the sine of 180 minus theta I. And so that's something you could just check in your calculator, or you could also confirm by drawing the unit circle and looking at the y value of the unit circle at theta and 180 minus theta. So if we go back to our right angle triangle here, we've got our angle 180 minus theta I, and so the sine of that angle is the opposite, which is d, divided by the hypotenuse, which is ri. So we know that the sine of this is the opposite d over the hypotenuse ri, but ri, we've already worked out, is square root of xi squared plus d squared. Okay, so what we'll do is we'll take this expression for a sine of theta I and sub it into here. So the magnetic field due to current segment I is equal to mu naught I over 4 pi delta x, and then sine theta I is going to be d, and then in the denominator we have xi squared plus d squared, and then multiplied by the square root of xi squared plus d squared from the sine theta. So when those two are combined, we get xi squared d squared to the 3/2 power, and then that's all in the k-hat direction. Okay, so that's not so bad. That is the magnetic field at point P, just due to the current segment that we've colored yellow. Now, what I want to figure out is the magnetic field due to all of the little current segments that make up our wire of length L. So the net magnetic field due to all current segments is B net is equal to the sum over I of BI, which is equal to, let's see, there's a whole bunch of constants. So we have a mu naught, an I, a D. Those are all constants for all of the current segments. So is 4 pi. And then we have the sum, let me write it like this, the sum of I of delta x, so all our current segments are length delta x, and then we have xi squared plus d squared to the 3/2. Okay, and then all of that's in the k-hat direction. So the next thing we can do is we can say, well, let's imagine that we make the current segments very short. So another way of saying the same thing is we're going to take the limit that delta x goes to 0. And if we do that, then the sum in the brackets becomes a Riemann sum, which we can express as an integral, so that b net is equal to mu naught I d over 4 pi times the integral of dx over x squared plus d squared to the 3/2. And that's going to be in the k-hat direction. And we're going to integrate from the left side of the wire to the right side of the wire. Okay. Now, this integral is maybe not trivial to do, but what we could do is we could look up this integral in a table of integrals. And if you do that, then what you end up with is, I'm going to actually do it this way. I'm going to say, let's take the d that's out front and we'll include it in the integral. So we're going to have a d dx over x squared plus d squared to the 3/2. And that turns out to be 1 over d x over the square root of x squared plus d squared. And we have to evaluate that between our limits of integration. Okay, so when we do that, we have the 1 over d, we have 1 over d out front. And then at the upper limit, wherever we see x, we're going to put an L over 2. So we have L over 2. And then we have the square root of x squared. So that's L squared over 4. Then we have plus d squared. And then we go minus, and x now is minus L over 2. Square root. X squared is the square of minus L over 2, but that's just plus L squared over 4 plus d squared. And so what we've got is two terms that look the same. We have minus the negative of the first term, which becomes basically the first term plus itself. And so this is equal to 1 over d. Then L over 2 plus L over 2 becomes L. So we could just write this as maybe L over d. And then it's 1 over the square root of L squared over 4 plus d squared. So if we multiplied this by mu naught I over 4 pi, that would be the current at a distance d above the midpoint of the wire. So B net is going to be equal to, let's see, we just have to multiply by mu naught I over 4 pi. So it's mu naught I over 4 pi L over d 1 over the square root of L squared over 4 plus d squared. And and then that's all in the k-hat direction. So it's kind of a complicated looking result. This is a vector, B net. And so if you think about it, really, I mean, you can't really imagine a situation where you have a wire of a finite length, L, with a constant current going through it. Because in order to establish a current in a wire, what would you have to do? You'd have to connect it to a battery. If you connect it to a battery, then it must be some kind of circuit loop, and so you can't have an isolated section of straight wire. So instead, what we could imagine doing is we could imagine taking a battery, hooking it up to a wire that's in some kind of loop, and so here's our negative terminal and here's our positive terminal, and then we can establish a current in that wire, which would depend on what the battery EMF was and what the resistance of this length of wire is. And then we could say, well, let's take now a point P that's very close to this wire. And in that case, what we could argue is that as far as this point P is concerned, it looks like it's very close to a long length of wire that has some current. And then over here, there's also a wire that has a certain current, but it's so far away from P that its contribution to the magnetic field is negligible compared to the contribution from the section of wire that looks like an infinitely long straight wire. So if we imagine that L is really, really long compared to D, i.e. we have, say, an infinitely long straight current, or equivalently, we have a big loop of wire, but we're looking at a point that's very close to it, then what could we do? Then we would say L squared over 4 plus D squared. So L squared over 4 plus D squared. We have that in our expression. In fact, it's in a square root. So if we made L really, really long, then we could ignore the plus D squared. Okay, so this would be approximately the square root of L squared over 4, which is equal to L over 2. So if we make that substitution in our expression, then we could say for a long straight current, B, a distance D away from the wire is, B is approximately, so what did we have? We had mu naught I 4 pi L over D, mu naught I over 4 pi L over D, and then we had the square root thing. So we had 1 over this square root, and so that's going to be 2 over L, and this is going to be in the k-hat direction. So we can cancel the L's. That's good, because if we had a really long wire, say L goes to infinity, we don't want an infinity in our answer. And then we have a 2 over 4, so that becomes a 1/2, and so this is equal to mu naught I over 2 pi D in the k-hat direction. Okay, or in other words, B, the magnitude, is proportional to 1 over D. So if you think back actually to our case of calculating electric fields for a long uniformly charged wire, so it's not a current, but just a static uniform charge on the wire, we found that the electric field strength decreased as 1 over the distance from the charged wire, charged line. And so we have a similar result for our magnetic field. Okay, so if we were to draw our long wire with some current I, then what we have is magnetic fields looping around, and it gets weaker as we move away, so the distance between adjacent field lines gets bigger and bigger. And then if it's a long wire, then the magnetic field looks the same no matter where you are along this length of wire. Okay, good. Now, that was kind of a, you can see that was a pretty long calculation. It was tricky because we had to think about how the cross product evaluated into a sign and the direction of it. Then we ended up with a bit of a tricky integral to do where we had a 1 over something to the 3/2. We had to look up our value in the table. Nevertheless, we got some kind of meaningful result at the end. Part of the reason that we did this example is because we're going to develop different techniques that we could use to calculate magnetic fields due to certain current arrangements. And in some cases, such as a long straight current, we'll find that this alternative technique is really quite a bit easier to use. So if you think back again to electric fields, we developed this technique of Gauss's law to calculate electric fields. And in situations where the distribution of charge had some obvious symmetry, we could take advantage of that to calculate electric fields due to long charged cylinders, a spherical distribution of charge, or a plane of charge. And so we're going to have something similar for our magnetic fields, which we'll call Ampere's law. Before we do that, I want to do one more example using this Biot-Savart law. And so we're going to calculate the magnetic field at the center of a loop of current. Okay, so this one is something where you could actually imagine that you could set up a loop of current. Oh, somehow I made a really straight line. I guess there's some way that you could tell it to draw a straight line. Did it by accident. Okay, anyways, here's an XY coordinate system, and I'm going to try to draw a circular loop of current, something like that. And so we could do that, right? You could set up a circular loop of current by taking a wire, bending it into a circle, and then inserting a battery at some point. So you cut the wire at some point and you stick a battery in there. And so I'm going to imagine that our current is going in the counterclockwise direction. So let's imagine we're here at the... Let's imagine we're at a point here on the y-axis and the current is in this direction. So we put our thumb in the direction of the current and we curl our fingers around and we say inside the loop we have a magnetic field that's coming out of the screen. And so if we're interested in what's happening at the center, we would say there is a magnetic field that's coming out of the screen at the center. Okay, and then we go look and say, well, there's lots of current segments in this loop. One of them is here at the left edge, and I put my thumb in the direction of that current. I curl my fingers, and we say, well, inside at the center of that loop, the field's coming out of the screen. And we take one at the bottom, and we put my thumb with my right hand in that direction, curl my fingers, and I say at the center of the loop, the magnetic field's coming out of the screen. And so no matter where we are, all of the different segments create a magnetic field that's coming out of the screen at the center of the loop. So that's the first thing that we observe. Okay, and then we imagine we take a little segment of this current, and so this is going to be delta S I, and it is in a direction tangent to our loop. Okay, and then we go from our current segment and we go to our observation point at the center, and that is a distance r away, and our r hat for segment I is along that radius pointing towards the center. Okay, so what position is our current segment at? Well, it's at a position xi on the x-axis, and it's at a position yi at the z-axis. Okay, so let's see if we could figure out then what is the magnetic field due to this segment of current. So the magnetic field due to segment of current I is mu naught I over 4 pi, that constant that we always have, and then it's delta Si cross with r hat I over Ri squared. And so we could say that this is Ri. Okay, let's first deal with delta Si cross r hat I, that's a hat, is equal to the magnitude of delta S times the magnitude of r hat, which is just 1, times sine of theta I. Okay, but if I reproduce our picture over here, delta Si is in this direction, and r hat I is towards the center of the circle. Because delta S is tangent to the circle and r hat is perpendicular, those vectors have an angle of 90 degrees between them. Theta I is equal to 90 degrees, and so therefore sine of theta I is sine of 90, which is just 1. And so that means that this cross product has a magnitude of just delta Si. We've already worked out that the direction of this magnetic field is out of the screen. We could also do that by the second right-hand rule number 2. We put our right arm in the direction of delta Si, curl our fingers so that it's parallel to r hat, and then our thumb points out of the page. And so we can say the direction of delta Si cross r hat I is out of the page, or out of the screen. And so we're going to call that the k hat direction. We imagine the z-axis is coming out of the screen. So we combine all that stuff, we get mu naught I over 4 pi, and then we have just delta Si over Ri squared and then it's in the k-hat direction. Okay, and so that's it. Then we say the net magnetic field due to all of those current segments is mu naught I over 4 pi, and then it's going to be the sum over all of the segments, and then it's in the k-hat direction. So again, we take the limit that delta S goes to 0, and we would say that B net is equal to mu naught I over 4 pi. So the sum becomes an integral of ds over r squared, and that's in the k-hat direction. Okay, and so this is going to be an integral around the loop. One of the things that makes this a pretty easy case to evaluate is it doesn't matter which kind of, where my delta S is in my loop, the distance from delta S to the center, is always the radius of the loop. So this r in this integral is constant. So we could say around the loop, the distance r to the center is constant. And if it's a constant, we could take it outside the integral. And so we get that B net is equal to mu naught I over 4 pi r squared, the integral of ds around the loop times k hat. But if we just add up all the little segments, the distance of those segments around the loop, that just becomes the circumference of our circle, which is 2 pi r, and therefore our B net is equal to mu naught I over 4 pi r squared times 2 pi r in the k-hat direction. And so we lose one factor of r, we lose the pi, and we have 2 over 4, which becomes a half. And so this is mu naught I over 2r in the k-hat direction. So this is the magnetic field at the center of a loop of current. So if we were to draw a loop of current, and so let's say it's going in this direction. Actually, I want to reverse the direction. Let's make it consistent with the problem we just solved. I'm going to take my current in this direction. Then, by the right-hand rule, the current creates a magnetic field that points up at the center of the loop. If we were to reverse the current direction, like so, then the right-hand rule, put our thumb in the direction of the current, our fingers curl downwards in the center of the loop, we would get a magnetic field that would point in this direction. There's also another way of doing the right-hand rule for the current loop. Imagine curling your fingers in the direction of the current. So on the left-hand side, we have if we're looking from above, we have a counterclockwise current, and so we curl our fingers in that sense. then our thumb points towards the top of the screen, and that's the magnetic field direction. On the right-hand side, if we look from above, we'd have a clockwise current. If we take our right hand and curl our fingers in that sense, then we have a magnetic field pointing towards the bottom of the screen, which is the direction of our thumb. One last observation before we complete this video is that we've calculated the magnetic field only at the center of the loop. We don't know exactly what the field looks like at other points. But it turns out that if I had a loop of current, we know that the magnetic field at the center looks something like this. And that may not be good when I convert this to a PDF. So let's put our B there. If you were to either, let's say you could map out the direction of the magnetic field lines using a compass around a current loop. I mean, that's something you could do. Then what you would find is that the magnetic field lines off center would have this kind of configuration. Now, if you look at that, that should be reminiscent of something that we've seen before. So this is the current direction. That looks a lot like what we saw for our bar magnets. Our bar magnets had a north and a south pole, and what we said is that magnetic field lines would come out of the north pole and they would terminate on the south pole. And so through the bar magnet, they'd go through the center. And we said that that was a lot like an electric dipole, and we drew magnetic field lines for our bar magnet that looked something like this. And so if we compare these two pictures, they're quite similar. And in some sense, the current loops behave a lot like a bar magnet. At least the magnetic fields that they produce are very similar to the dipole magnetic fields that we get from a bar magnet. Okay, so that's where I'm going to stop this video, and the next time I post a new video, what we're going to try to do is we're going to try to develop Ampere's law, which is going to give us another method for calculating magnetic fields due to different arrangements of currents. And we're going to find that in some cases it's a lot easier to use than what we've seen with this Biot-Savart law. However, it's worth keeping in mind that Ampere's law is not always going to be easy to use, and there are some cases where, like this current loop that we just did, where Ampere's law is really the method that we have to go with. All right, so thanks very much, and we'll talk to you next time.